السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. This is the second and I hope the last session of the last part of the sampling session. Last time we covered types of sampling, right? I think we covered 4 types of sampling. Do you remember them? Systematic is one, deterministic, random, and sample of convenience. Okay, so with 4 types that we covered last time. What are the differences between them? So let's start with the deterministic sample. When can we say that this sample is deterministic? If we know earlier, you mean if we know in advance what will be the elements in the sample. Okay, in other words, we can say if there is no chance in the process, if we determine exactly what will be the elements that will be in the sample, so then this is deterministic. There is no randomness at all. There is no chance. So this is deterministic. The second one was systematic, right? So what is systematic sampling? So it's random in the first step, but then after we select the first one, all the elements are determined after that. So they are dependent on how we selected the first one. Okay, so still it's not random, so it's called systematic, and it's not deterministic fully because we don't know in advance which will be selected, but it's kind of mix of these. The last one, the third one was, so we said deterministic, systematic, then sample of convenience. So what is sample of convenience? So the example that we gave last time was sampling from the students that are coming to the class. Okay, the problem is that generally this kind of sampling, we might not know the population and we might not know the probabilities of getting any of the elements or individuals in the sample. Okay, so the fourth type, which is random sample, covers this. So for a random sample, we need to know the probability of every element being in the sample and every subset of elements being in the sample in advance. Okay, and if that's the case, then this is a random sample. And I think we covered these types last time, and now we'll talk about distributions. So you are familiar with what we call probability distribution. So what is a probability distribution? We have a quantity, a random quantity that has several possible values. Okay, so we have a quantity that has several different values, and the probability distribution that over this random variable or random quantity has determines two things. First, what are the values, the possible values of that quantity? What are the possible values of that quantity? And for each value, what is the probability for that value? Okay, and for example, the number of the example that we I think saw last time, number of if I roll the dice twice, what is the number of even numbers I will get? So I'll get 2 numbers, right? What is the distribution of a random variable that will indicate the number of even numbers I will get when I roll 2 dice? Okay, so it might be one of multiple cases. So what are the possible values in this case of that random quantity? No, it's not 2, 4, 6. We cannot get 4 even numbers, right? When we roll 2 dice. So what are the possible values in this case? We have 2 dice. We will roll them. Okay, maybe one after the other. How many even numbers I will get as an outcome? So that's the maximum, right? The maximum is 2. What are the other possible values? 1 or 0, right? So 0 or 1 or 2. Now each one of these possible values has a probability, right? So the framework that indicates what are the possible values of a random quantity and what are the probability for each of these values is what we call probability distribution. And I think you are used to that in many other courses, right? In any probability or statistics course, you know what we mean by probability distribution. And if we can do the math, if we can compute these probabilities, then we don't need to do any simulation. Okay, as you will see in this lecture, simulation is a powerful tool to get probabilities, okay, without calculating them. But if we can do it, then we don't need to do, if we can do it mathematically, we don't need to do any simulation, right? But many cases, the calculations of probabilities are not that easy or might not be that trivial. And as you saw, I think, previous lecture or the lecture before, the Monty problem, right? Some of you or many of you were confused thinking that it's 50-50 chance, but it's not. Okay, and we saw that by doing the simulations. That's why most of the focus today will be on simulation, because it's in many cases it's easier than doing it mathematically. So that's probability distribution. Now the other type of distribution that we cover today is called empirical distribution. Empirical distribution, and empirical means, generally the word empirical in the context of data science means based on observations. Okay, so empirical distributions are not based on mathematical calculations. Okay, they are all based on observations. Okay, we will do an experiment multiple times and we observe some values, and based on that we have a distribution, and that distribution will be called empirical distribution. So yes. Usually, yes, based on mathematical calculations or based on the entire population, as we will see. Okay, but you can think of it for now, it's based on mathematical exact probabilities. Empirical distribution can be estimated from repetitions of an experiment, as we will see inshallah today. So the empirical distribution determines two things. Remember, the probability distribution determines also two things. It determines the probability, the possible values of the random quantity and their probabilities, right? Here we have all observed values of the random quantity that we are measuring. Okay, notice the difference. In the previous slide, we saw all possible values. Here we see all observed values. What is the difference between these two? What is the difference between possible values and observed values?
Possible values, we don't know in advance would be observed.
Actually, it's the opposite. Okay. Possible values, we know in advance that the possible values of getting, in the example that I told you, it's 0 or 1 or 2, right? But if we roll the dice, we might not observe all the possible values. We might always, for some time, get either 0 or 1. Okay, might not get 2. Okay, in the experiments that we do, right? So it's not guaranteed that we see all. So observed values are actually a subset or superset of the possible values. Okay, we might not observe all possible values in it's generally subset, but it might be the same set. Okay, and for each of the observed values, we observe the proportion of times that each value appears. Okay, how many times relative to the total number of times that we run the experiment? How many times we observe each value? If I know this proportion, then I know kind of the probability of observing this value, right? Right? So this will be called the empirical probability in this case, because we calculated it by counting from what we observed, not from a mathematical calculation. Okay, we'll see examples now. I hope that they will make things much more clear. So we'll start with die that has 6 faces. So we'll put them in a table from 1 to 6. Okay, so this is the 6 possible values. When I roll one die, I will get one of these 6, right? Okay. Now, if I plot the histogram, of that table, what should I get? How many columns we have here? Just one, right? So we have just one column. So we should get the distribution of that column, right? So what is the distribution of that column? Huh? Yes, what will be the distribution? It will be equal. What do we call distribution that every element, every possible value has an equal probability? What do we call it? Uniform, not normal, uniform distribution. Okay, so you will see something like this. Everything is equally probable, right? So that's a uniform distribution, right? Because every one of these appeared just once, right? Now, is that a probability distribution of seeing the number that when we roll a die, or an empirical distribution? Why is it empirical? Did we try? Did we do any experiment? Did we repeat any experiment? Did we observe anything? Where is the simulation? We didn't do the simulation yet. Okay, we didn't do anything. It's just the values, the possible values, right? And because we draw the histogram, each one appeared here once, just because the way that we put the numbers in the table, we got this distribution. So this is actually the probability distribution, right? Because the probability of every number here is 1 over 6, right? When we roll the one die, you will get a number, and that number has the probability of 1 over 6, right? And every one of these has 1 over 6. So that's actually the exact probability distribution of that random variable. The random variable here is just the number that we see when we roll a die. Okay? With me so far? Yes. The possible values are from 1 to 6. Yes.
And the probability for each, we will take the percentage unit or what?
Yes, the probability, if you don't see that, what is the probability of getting 4 when I roll a die? 1 over 6, 3, 1 over 6, 2, 1 over 6, right? All of them are 1 over 6. And that's just a visualization of that distribution. Okay? All the probabilities are 1 over 6. Oh, so are you saying that these numbers are not 1 over 6? Yeah. Ah, okay. That's your question now, right? So why don't we get 1 over 6 here? Remember the height of a histogram? What is the height of a histogram? Yeah. Where is the probability here? The height is the density, yes. So, but where is the probability here? The area. Very good. So the area here is the probability, okay, or the percentage. So the percentage is, let's say that this is 16.67. Actually, it is 16.67 times what? So that's the height. The width is 1. Remember here, the bins have 1 width, so that's the percentage. Okay, so 16.67 over 100, that's the probability of each. Okay, now let's do that. Let's do a sample of 10 elements. So, let's do a 10 sample. Let's sample 10 numbers from that experiment. So the sample method here is a method over the table in which we sample number of rows from the table. Okay, remember last time we saw another method, right? It was numpy.random.choice. Okay, and that one, given an array, it will select elements from that array. This one is working on a table directly. It will select rows from the table with replacement. Okay, so sample of 10 means sample 10 times from the table with replacement, which means that we might see repetitions. Okay, so if we do that sample of 10, which will return another table, we'll get something like this. So this is 10 samples without without repetitions. Yes, with repetitions. Sorry, with repetitions. Did I say without repetition earlier? Sorry. Okay. So sample by default does sampling with repetition. Okay, with repetition. Sorry. Yes. Works on arrays. Works on an array. The choice method works on an array. Sample works on a table. Okay. Yes. With repetitions also. With repetitions. This one also, I said with repetitions, and there is a parameter that you can set to make it without repetition if you like. But by default, it is with repetitions. Okay. Now we sample 10 times from that randomly. Okay. Now let's see the distribution that we will get from that sampling. So it's like we roll the die 10 times, and we observe the value that we see on the face. Okay. These are the values that we see. Let's see if we draw the histogram. Of course, we'll call sample here again, so it might not be exactly the same numbers, but it's like that. We get 10 samples and we do the histogram. So here is a histogram out of the 10 samples. Now, is that an empirical distribution or probability distribution? Empirical, right? Right? Why is that? Because it's based on observations. Okay, so we did the experiment 10 times. Okay, we rolled the die 10 times or got 10 samples from the possible values, and we got this distribution. Now, how similar this distribution to the probability distribution that we saw earlier? Is that similar to it? No. Are not equal. Okay, is it close to them or different? They are different, of course, right? So this doesn't look like uniform at all. Okay, let's do it again. Maybe you can get something different. How about that? Is that similar to the exact? Okay. How about this one? Oh, sorry, not this one. Okay, this one again. Okay, so every time we get the sample, we might get different distributions. So these are empirical distributions. Okay, but let's increase the sample size and see what will be the distribution. So we increase the sample size to 1,000 now. What does that mean? It's like we roll the die 1,000 times. Okay, and let's see what will be the distribution. So we get this distribution. How similar is that to the previous one? It's much better, right? It's much closer to the previous one. So it seems like doing the experiment more, getting more samples, gives us better or closer distribution, closer empirical distribution to the probability distribution, to the exact distribution. Remember, the exact distribution was equally probable for all possible values. Let's see what happens if we increase it even to, what's this? This is 100,000. 100,000. We'll get this. So that's even closer, right? Okay, so what does that mean? Did we use any mathematical computations here? Nothing, right? We don't, of course, the problem is easy, right? We can easily say the probabilities are 1/6, okay? But the concept here is that without doing any mathematical computations, just by sampling and showing or visualizing the distribution, the empirical distribution, we can get a distribution that is closer to the probability distribution. But there is a condition, right? What is the condition here? The sample size. Okay, the sample size. If the sample size is small, then we get something like this, which is not close to the probability distribution. If it's large enough, we can get something like this, which is almost exact. Okay, now let's get back to the slides, and we will generalize this concept. we generalize it in what we call the law of averages or the law of large numbers. So what is this? It says that if a chance experiment is repeated many times. So what do you mean by chance experiment? Random. Okay? So experiment on random samples. If a chance experiment is repeated many times, independently and under the same conditions. So what do you mean by independently? So we said that the chance experiment is repeated many times independently.
Doesn't depend on the experiment before.
Yes, so every experiment, every time we repeat the experiment, doesn't depend on the previous ones. Okay? Which was our case here, right? Okay, so if the experiment, the outcome of the current of the new experiment doesn't depend on the outcome of the previous experiments, okay, which means that they are completely independent, and under the same conditions. What do you mean by under the same conditions here? Sample size and also the probabilities, right? If we change the probability somehow, then this is not under the same conditions. For example, if we say that but of course it won't work with the die, but with the drawing tickets, if it's without replacement, then these are of course under different conditions, right? Because the second one will have a different probability distributions than the first one. Okay? Sorry? Okay, if we when we draw tickets from randomly, okay, with different colors, if we say that we'll do that twice without replacement, then the second draw will depend on the first draw, right? So the distribution, the probability distribution will be different. So again, if a chance experiment is repeated many times independently and under the same conditions, then the proportion of times that an event occurs gets closer to the theoretical probability of that event. Okay, so if we repeat the chance experiment many times, independently and under the same conditions, then the proportion of time, the percentage of times that we see an event occurring, okay, will get closer to the theoretical, that theoretical here means, of course, we can compute it mathematically, it will get closer to the theoretical probability of the event. Okay, so doing that experiment many times, as we see, will give us closer to the theoretical probability. And this is the example that we just saw. As you increase the number of rolls of a die, the proportion of times you see the face with 5, actually you can do that with any other number, with 5 spots, gets closer to 1/6 as we just saw.
Doctor, so
yes?
Let's say that we do the empirical distribution many times, and the same condition you will get close to the probability distribution.
Okay, so let me correct that a bit. We will not do the empirical distribution many times. We will repeat the experiment many times. When we repeat the experiments many times and we get several observations, the distribution of those observations, which is the empirical distribution, will be closer to the probability distribution. Okay? We can say it, and this is exactly what we will say now in this slide, talking about the distributions now. If the sample size is large, then the empirical distribution of a uniform random sample resembles the distribution of the population. Okay, which means that the empirical distribution will be very close to the probability distribution, the theoretical probability distribution. Of course, with high probability. Okay, it might not be very close at the end, just by chance, but with very high probability, as the sample size increases, you will get a distribution that is very close to the probability distribution. Let's see another demo. I hope that will make the idea more clear. Remember the flights dataset that we saw in the previous lecture? So here is the flight dataset. Each row is a flight with a destination and with a delay, okay, of taking off delay. We have about 14,000 rows here. Now let's let's visualize the distribution of the delay time. So we have bins around the range that is of the delay column, and let's see what we will get. So this is this is the distribution of the delays from the original data set. Okay, what do we notice here? Anything that you notice here from the histogram? Is that a uniform distribution? Of course not, right? Okay, so most of the cases are in this area, right? Okay, and there are rare cases when we have a delay over than maybe 100 and 130, right? Of course, here the focus is on this range only. There are other values which we can consider as outliers, but looking at this range, we see that most of the flights are delayed within that range, right? Okay, just to know the range, the actual range, we will compute the minimum, which is minus 16 here. We said that minus 16 means the flight left earlier, which rarely happens, unfortunately. I don't know, unfortunately or fortunately, but the minimum is minus 16, the maximum is 580 minutes. Okay, but as you see, as if we even visualize it up to 500 or 600, most of them will be zeros and very rare cases, as we already see here. Now, the average of them, of the delays, is about 16.6. Okay, now let's get a sample of 10 flights. Let's get a sample of 10 flights and look at the distribution of the delays within that sample and see if that will be similar to the distribution that we see now or not. So we'll sample 10 and then we visualize the distribution. So this is what we get. Is that closer to the original distribution or not? It's not, of course, right? It's not. If we do another sample, again, it's not. Third sample, it's not. Okay, fine. What should we do? Increase the sample size. So let's increase the sample size to 1,000 now. Okay, so we'll do 1,000 sample. This is with or without replacement? With. Okay, with. By default, sample is with replacement. Okay, so if we do that and we visualize that sample, we get something like this. Okay, just to remember the original distribution, here is the original distribution. So this is empirical or probability distribution? This is empirical. Okay, and we can say that this is a probability distribution assuming that the data set has the entire population, so that's actually the exact distribution, and this is the empirical. Are they similar or not? They are very similar, especially in that range, right? But for rare cases, they are not very similar. Okay, not very similar, but of course they are close, but they are not very similar, and that's usual. Okay, for the rare cases, it's very hard to get close to the exact probability, but for the popular cases, as you increase the sample size, you will get very close. Okay, any questions so far? Okay, very good. Now let's continue and talk about parameters and statistic. Or yes.
The last will be empirical and probability. This one.
This one is from the original data set. So this one, the probability distribution can be considered, assuming that the data set is the population. No, this one is the probability distribution. This one is empirical because we got a sample here. Okay. Any other questions? Sorry? What do you think? Okay. What do you think? If we get a sample and from the sample we draw distributions of the observed value, then this is empirical or probability? Empirical. That's the definition of an empirical distribution. Yes. Okay. So statistics and parameters, they are all very connected to inference, and especially statistical inference. So statistical inference is about making conclusions based on data in random samples. So for example, we use the data, we have data set, and we want to know a specific quantity out of this data set. For example, the average GPA of the students in this class. Okay? I might not know it, so it's unknown, but of course it is a fixed value, right? If I know the values for the entire population, then I know the exact average GPA of the students in this class, right? Okay, so that's a fixed value. Now I want to get an estimate of this unknown quantity. So the unknown number about the data is fixed. The estimate depends on the random sample that I will get. So I have a population. That population has specific quantity. I might not know it, but it is fixed. There is a number that I don't know. Okay, but it is one number. That is called the parameter of the data. Okay, as we'll see next slide. That's called a parameter. Now I want to estimate the value of that parameter. I will do this estimation by random sampling. So I will do a random sample, multiple random samples, and compute some values out of these samples. From that I can estimate the value of the unknown quantity. Okay, and of course the estimation will depend on the random sample that we are doing. So the parameter is the number that is associated with the population. The statistic is the number that is calculated from the sample. So the statistic is actually an estimate of a parameter. So the parameter of the class students now is the average GPA. That's a parameter. Okay? Now I can get a sample from you, and from that sample I can compute the average GPA of that sample. The value that I compute is called a statistic. And that statistic is an estimate of the actual value of the parameter. Okay? So you see the difference between a parameter and the statistic. So the parameter is the quantity that is associated with the population. The statistic is a quantity or a number that is computed from a sample. The parameter is the average, the actual average of the GPA, okay, of the entire population. The statistic is the average GPA that I will compute from a sample of you, okay, which will be an estimate of the actual parameter. Is the difference clear now? Yes.
We can say the parameter is the variable and the value is for one sample, linear or whole.
Fine. Can I answer this after seeing the demo? Maybe it will be answered already. Okay. So let's see that demo. So this is a similar example to this GPA, but on the flights data set. Okay. So instead of the average GPA, I want to compute the median of the delay of the flights. Okay. You know the median, right? The value that is in between. If we ranked all the, if we sorted all the delays, the value that is in the middle is the median value. So the actual median value of the data set of the population is 2. That's the median delay over the entire population, assuming that the data set is the population. Okay? Now let's assume that we don't know this value. We don't know this value. So we want to estimate it. We want to estimate it. So this value is what? The parameter or the statistic? The parameter. Okay, but we don't know it. We'll assume that we don't know it. So we will sample 10 flights from the data set, and we compute the median from them. When we compute that value, is that a parameter or a statistic? It's a statistic now because it's computed from a sample. Okay, let's do that once and see what the value will get. We get 1.5 here. If we run it again, should we get the same value? We'll get, oh, we got the same value. That's weird. That's something weird here. Okay, it appeared twice, but as you see, we will get eventually different value, right? So every time there is a probability that you will get different value. Okay? So all of these are statistic. Are different values of the statistic. Yes, it is trying to estimate. By this, we are trying to estimate the actual value. Okay? Now, if we do that multiple times, as you see, whenever we do this sampling, we get a value, right? If we do that multiple times, we will get different estimates, right? We get several estimates. Okay? Now, if we draw the distribution of the estimates, then we can see the probabilities. We can see how similar it will be to the actual value of the parameter, which we know it's 2, but we will assume that it's not known. So let's see that. We'll do that simulation. So an experiment here will be to sample a specific number of flights, and we compute the median from them. Okay? Whenever we compute the median, that's a statistic value. So calling this with 10, we'll get one value. Here it is -2. If we call it again, we might get a different value, and so on. Okay? Now, we'll do that. Look at that code. What are we doing here? So look at this. What are we doing here? Mariam?
We are collecting the number of estimates and save them.
Yes, so this is a loop that will be repeated 1,000 times. Okay, in each iteration of the loop, what are we doing?
We are adding
We are getting a sample and we compute the median of them. So this is just one estimate. And we repeat that 1,000 times. And we, of course, we append each value to the array. So eventually we will get what? An array of 1,000 estimates. 1,000 estimates. Okay? So running this, we'll get 1,000 estimates. Now we can just add them to a table just to visualize them with a histogram. So we'll see a histogram of these values now. We'll get this. Okay? So what is this? We want to understand what this is. So this is a distribution. This is empirical or probability distribution first? This is empirical, of course, right? We got that from observations, from running an experiment multiple times. Okay? Now, each experiment is a sample, is computing the median over a sample of 10 flights. Okay? So this is just an estimate. We got that estimate, we get values of that estimate 1,000 times, and we compute, we draw this distribution. Okay? So this is how we got this distribution. Is that clear? Okay. Now, what do we see here? What do we notice here? We know in advance, of course, just for that example, we know that the median is 2, right? Is that far from that or from that distribution or not? So it seems like the most probable is here, right? It's like maybe -1 or 0, right? What do you mean by not sorted? It's the x-axis is sorted, of course. Okay, it's a histogram. Okay, don't forget. So it seems like the most probable value is this, and the other values also have good probabilities, right? The distribution is not very biased. It has a range, right? So that's not very. It doesn't seem that the distribution really resembles the exact distribution. What should be the exact distribution in this case? It's only one value, right? 2 has the whole distribution and everything is 0. Because we know that the median is 2, right? But here, from the sampling and running the experiments 1,000 times, we got this distribution. What should we do now? Should we increase the sample size? Okay, so let's increase the sample size. Instead of sampling just 10, remember here we sample 10 and we repeat that 1,000 times. Here we will sample 1,000 and we also repeat that 1,000 times. So how many values will we get eventually from here? Still 1,000, but now each one is computed over a sample of 1,000 flights instead of 10,000. Okay, so each estimate here, or each statistic, is computed from a sample that is larger, much larger than the previous one. So let's do that and see the distribution. What do you expect about the distribution here? It should be closer, right? It should be closer to the actual distribution. So let's see that. So here is, oh, it's still running. Okay, so here is what we get. It's much better than the previous one, right? Much better. Okay, now the probability is focused on two values. I think this is 1, this is 2, 2 and 3. And now 2 is the most probable one. Okay, so what did we do so far? We have a population, okay, and there is a quantity that we don't know the value for it, which is the parameter of the population. We want to estimate that value. We get a sample. From that sample, we get an estimate, which is the statistic, and we repeat that multiple times so that we can get a distribution. We can get an empirical distribution of that statistic. Okay, and here is what we get. Okay, any question about this? So this is the summary of what we did. Probability distribution of a statistic. The values of the statistics, of course, vary because of the random samples. Now we can, to get the probability distribution, we need all possible values of the statistic and all corresponding probabilities, but that might be hard to calculate. So if you think about this example, the median, if I want to compute the exact distribution of the median, then I should consider all subsets of the population and compute the median for, and then get the exact distribution of the median. But that's not easy. Okay, by simulation we can do something like that. Okay, and if I have a population and I want to compute what is the probability that the median will be that value. Okay, I have to compute that for every possible subset of the population in order to get mathematically the exact value for the exact probability for that value of the median. Okay, did you get that?
What is the subset?
Okay, if I have a population, okay, I can compute the median just in one value, right? If I know all the information I want. But if I want to compute the distribution, the possible probability distribution for the possible values of the median, okay, then I have to get every subset from the population and compute the median for it, and then from that I can compute I can visualize the distribution. This is computationally very expensive. So we do that through simulation. This is what we just did. So for simulation, we get, instead of getting the probability distribution, we get the empirical distribution of the statistic. And that will consist of all the observed value of the statistic instead of all possible values. And it will be a good approximation to the probability distribution if the number of repetitions in the simulation is large. As you saw, when the sample size was 10, we get a distribution that is very far from the actual one. And when we increase the sample size, we get much better distribution that is much closer than to the original one. And here is a quick demo that has a nice visualization. So here is the same, again, data set, but instead of looking at one sample size, we will look at 3 sample sizes now. Okay, we saw 10 and 1,000, right? Here we will see 10 100, and 1000. And for each, we repeat that 2000 times. Previously, we repeated just 1000 times. Okay, so do you understand what we are doing here? So previously, we ran one experiment 1000 times, and the experiment was to take a sample of 10 flights, then compute the median. That's the first one. And the second one, we increase the sample size to 1000. Here, we will do like 3 things in parallel. We will do samples of 10, samples of 100, samples of 1000, and we repeat that 1000 times. So eventually, we'll have 3 arrays instead of 1, 1 for each sample size. Okay, but still the length of each array is what? Is the same, which is, no, it's not 1000 here, it's 2000. Okay, it's 2000. Okay, so you understand what we will do here? Is that clear? Okay, now we'll run this. So we'll have 3 arrays, and we will just put them in a table. So it's still running. Done. Now we put them in a table, and we visualize the histogram. Now remember, when we visualize the histogram, we used to give the name of the column which we want to visualize, right? If you don't give the name of the column, it will visualize all of the columns. Okay, overlaid. I think we saw an example before. Okay, how many columns we have here? 3. Which is when the sample size is 10, when the sample size is 100, and when the sample size is 1000. Okay, so this means that what we will see now is 3 distributions overlaid. One when the sample size is 10, one with 100, and one with 1000. Okay, now let's look at them. Here is the 3 distributions. Okay, so the blue one is when the sample size is very small, which is 10. Okay, so you see that the distribution is kind of flat. Okay, it's not a good estimate. When we increase the sample size to 100, which is the yellow one here, it's getting better, right? It's getting better focused towards the actual median. The range is smaller. Okay, it's less flat. And then when the sample size is 1000, it is very focused to probably 2 values. I think it's just 2 and 3 here. Even the highest probability is the one that we saw from the population. Okay, if you have time, you can increase the sample size to be 10,000 or so, and run it and see how the probability how the empirical distribution for this case will be. It will get closer and closer to just 1 bar. Almost 1 bar at 2. Okay? Any questions about that? So with that, we are done with the sampling session, which is session I think number 8. Next time, inshallah, we'll start a new session. Any questions before we finish? Okay, thank you.